All right, last one. So, what have we done so far? We've gotten explicit formulas for the following functions: sine of cosine inverse of x and cosine of sine inverse of x. And I alluded at the beginning that we would figure out how to get formulas for anything of the form trig function of inverse trig function. And, well, if it took about 10 minutes for each of these two, I obviously don't have time to go through the remaining of them, because, right, how many trig functions are there? Well, there are 6 of them. There are 6 inverse trig functions, so that would be a total of 36 options. So I won't try to go through and get you formulas. Instead, I'll try to give you ideas for how you can get formulas. So I think I'll do this one in 2 different, let's try to compute the cosine of the inverse tangent of 4 over 5. So let's do it. So I'll follow the exact same strategy as we used before. I'll take theta to be this angle. Then what do I know? I know that tangent of theta is equal to 4 over 5. I also know that this angle is in the range of inverse tangent. So theta is in negative pi over 2 to pi over 2. And let's go ahead and, that's a really bad job of writing, is in 2 watts. So that's quadrant 1 or quadrant 4. Either way, I guess cosine of theta is positive. So we'll just remember that at the end, because there will probably be like a plus or minus that shows up. So there are 2 strategies that are worth looking into, one algebraic, one geometric. I'll go for the algebraic strategy first. So since tangent of theta is equal to 4 over 5, that tells me that sine theta over cosine theta is equal to 4 over 5. And I want to know what the cosine of theta is. So I want to know cosine theta. So here's what I'll do. I'll express sine in terms of cosine using this, because I also have the Pythagorean identity that I'll be able to use. So I guess I can figure out what sine of theta is. I can solve for sine of theta by multiplying cosine of theta over to the other side of that equation. So doing so will give me sine of theta is equal to 4/5 times the cosine of theta. All right, so the other thing that I know is the Pythagorean identity. The Pythagorean identity tells me 1 is equal to the cosine squared plus the sine squared of theta. And I know what the sine squared of theta is. I know the sine squared of theta is 4/5 times the cosine of theta. So let's make that substitution. So this will give me 1 is equal to, I'll leave the cosine alone, cosine squared of theta plus 4/5 cosine theta squared. Nice. So all I've done is I replaced that sine of theta with 4/5 cosine of theta, because I know they're the same. Carrying on, let's see, that will give me cosine squared of theta. I'll leave this piece alone still. And I guess, how do you evaluate the square of a product of a quotient? Well, you can just square each piece. So that's plus 16 over 25 cosine theta. Squared, that's squared too. All right, so we can factor out a cosine squared. That's equal to cosine theta squared times 1 plus 16 over 25. So that's 25 over 25 plus 16 over 25. That is, I guess, 41 over 25. All right. So let's carry on down to the next line. So now I know cosine theta times 41 over 25, right? What I did in that step is I replaced this with that because they're equal to each other. So that tells me, summarizing this big long line, that 1 is equal to cosine squared of theta plus 41 over 25. So right now I have 1 equals cosine squared of theta times 41 over 25. I want to know what cosine is. So, I mean, I know how to solve this for cosine. I'll divide this over to the other side, and then I'll take a square root. So doing so gives me cosine squared of theta equals 25 over 41. So cosine theta is equal to the square root of 25 over 41. And you might be thinking, well, there should be a plus or minus there, shouldn't there? But let's just go above. This angle theta is in the range of inverse tangent, so that angle theta has to be between negative pi over 2 and pi over 2, quadrant 1 or quadrant 4. In quadrant 1 and quadrant 4, cosine is positive. So, no, there's no issue. It's positive. So there's the answer, but it's not a complete answer because I see a fraction inside of a square root. So I should simplify that. That'll be cosine of theta equal to the square root of 25 over the square root of 41. And I see a perfect square in the numerator, in the square root inside of the numerator. So the numerator is just 5. And the denominator is the square root of 41, so there's a square root inside of the denominator. I don't want there to be a square root inside of the denominator. I need to rationalize the denominator. I will multiply and divide by the square root of 41. So, doing that, multiplying and dividing by the square root of 41 leaves me with 5 square root 41 all over 41. So that means the cosine of the inverse tangent of theta, of the inverse tangent of 4/5 is equal to the cosine of theta. I just computed that to be 5 square root 41 over 41. Cool. Now let's go up and use this triangle strategy. So theta is an angle in quadrant 1 or quadrant 4 whose tangent is 4/5. So there's the picture, and the tangent is 4/5. But notice up in quadrant 1, tangent is positive. In quadrant 4, tangent is negative. So it has to be in quadrant 1. So this is an angle in quadrant 1. That's the type of angle that I can see inside of a right triangle. So let's use that. I'll draw this angle theta inside of a right triangle. So there's the angle theta. I know that the tangent of this angle theta is 4/5. Tangent is equal to the opposite over the adjacent. So opposite over adjacent is 4/5. Writing that, 4, 5. And I'll label that with h, because apparently I will need h if I want to compute cosine of theta. So let's compute h. H squared is equal to 4 squared plus 5 squared. 16 plus 25 is 41. So h is the square root of 41. Now I need cosine of theta. Cosine of theta is equal to adjacent over the hypotenuse. Well, the adjacent is 5. The hypotenuse is the square root of 41. And what did I just do before to get rid of that 41 in the denominator? Well, you need to multiply and divide by the square root of 41. Great. So that completes this lecture. If you want to compute trig function evaluated at inverse trig function, either you can say, well, this problem is equivalent to saying, I know what one trig function is, I need to know what another trig function is. There's an algorithm to do that. We've done that a few times. Or you can say, well, I know what one trig function is. I can encode that fact in terms of a triangle. I can now use that triangle to compute the trig function that I would like to know. Those are the two basic strategies you have. So there are a few homework problems assigned that give you examples of this type of stuff. Happy hunting! See you in the next one.